Hello there, welcome back to Differential Equations by Alexander. Okay, so today I want to talk about exact differential equations. I want to explain what they are, and then in the next video I will give some examples on how to solve them. So before we move on, I want to recall that the first type of equations, the first type of differential equation that we learned how to solve were separable equations. So for example, the equation here in the red box, that is an example of a separable differential equation. Now, if you just change the formula just a little bit, now you have a differential equation that is not separable, and also it is non-linear. But now we want to say that this is an exact differential equation. But before we do that, I want to go back to a little bit of a calculus to see how this is coming about. All right, so again, this is the differential equation that we are interested in now, but just because we have a formula multiplied by dx and a formula multiplied by dy, it does not mean that this is an exact differential equation. So it's a little bit more going on behind this. And so what I want to do is I want to look at the function that is in the very top, and let me put that in blue. So this function f on the very top, so this is a function that you would see in calculus 3, vector calculus. And so now the question is asking us to find the partial derivative of this function. All right, so let's just do a little bit of calculus 3 here. So the derivative of f with respect to x. So differentiate the function with respect to x, then you'll get 2x minus 5y. All right, so that's your partial derivative of f with respect to x. And now differentiate the function, separately differentiate the function with respect to the y variable. And so the derivative of f with respect to the y becomes negative 5x plus 3y squared. All right, so now what do you notice about this formulas that we just got by doing a little bit of calculus 3? So notice that those are the same formulas that you have in the formula that we are saying that this is a differential equation. And so what I want to say is this: the differential equation that is given to us is of the following format. You have a function f, and if you differentiate it with respect to the x variable, then you multiply it by the dx, the differential dx. And now the other piece is the differential derivative of f with respect to the y, and multiply by the dy, and then you just put this equal to 0. And so your differential equation that you have on the very top, this is a very special type of differential equation, and it is a special type where the first component and then the second component, they actually come from a function f. Okay, they come from a function f, and then you have to do a little bit of calculus 3 to get the two components. All right, so hopefully that motivates the definition that we're going to have next. So here are the definitions. And so what we were saying is this: suppose that you have something that an expression that is of this format, a function m multiplied by dx and a function n multiplied by the dy. So this expression is going to be called an exact differential if there is a function f such that the first component is equal to the first derivative of f with respect to x, and the second component, the n, if that is the derivative of f with respect to the y, like we had in the example. So if you do have an expression of this format where there is some function f that if you differentiate in a specific way, and you get the first component and the second component, the n, then it will be called an exact differential. Notice that this is just an expression right now. Now the next definition is about the differential equation. So we have the expression, but now we make it equal to 0. And now this is going to be called an exact differential equation if this thing is an exact differential, right? So hopefully that motivates the idea behind the exact differential equations. So we have something that looks like this in the red box, but this will be called an exact differential equation if there is some function f that satisfies these two properties about the m and the n that was explained in the example. All right, so now the question that we have is actually backwards from what we have seen. Okay, so the equation that we have usually is of the following format. You have the m, some function m multiplied by dx, and some function n multiplied by the dy. You make it equal to 0. And so you have this equation, and in the very beginning, you don't know whether it is an exact differential equation. And so the question is, how do you know that there is a little function f such that it will give you the m and the n after you differentiate with respect to the x or the n? Well, that's what the theorem is telling us, okay? The theorem is telling us when is this expression, or when is this equation an exact differential equation? So it gives you a little test to to figure out whether this is an exact differential equation. And the conditions are the following, and I'll just say it here: the m, the n, and the derivatives, they have to be continuous on the specific domain given to you in the problem. And then the other thing you have to check for the differential equation to be exact is that you have to differentiate this m and the n in this following format. Notice that the m is next to the dx, and then the n is next to the dy. But when you go down to the test of the theorem, when you go down to the test of the theorem, you differentiate the m with respect to the y variable, and then you differentiate the n with respect to the x variable. So it's kind of like flip-flopped. And so if these two things are equal to each other, then the differential equation is exact. Okay, that means that there is some function little f that kind of gives you the m and then the n. All right, so if you have taken calculus 3, some vector calculus, what that means is the following. So this is related to calculus 3. So here's the little function f that we start off, and then we differentiate. There's suppose that the function is a function of two variables. And so you can differentiate with respect to x, and you get this derivative. If you differentiate with respect to the y, then you get this derivative. Okay, and so for each function here, so for each derivative, this is now a function, and so you can differentiate this in two different ways. Differentiate the red box with respect to the x variable or with respect to the y variable, then you get the second derivatives. Now the same thing for the other side. For the derivative of f with respect to the y, you can also differentiate with respect to the x and differentiate with respect to the y, and so you get this second derivatives. And so what the theorem is telling us, that we have to look at the following information. We look at the second derivatives of the function f, and then what we are saying is that these two things are equal to each other. Okay, and so if the function f and then derivatives were continuous, then the theorem, roughly speaking, is saying that all we have to do is that we have to check that these two blue things are equal to each other. So that's what the theorem is saying. But now, kind of translating this back into the differential equation. So what we're saying is this: this is our m, and then this is our n. And so what we're saying is this: and then this will be the partial of m with respect to the y variable, and then this is the partial of n with respect to the x variable, and then we're saying that those two things are equal to each other. All right, so that's just a little picture of what the theorem is saying. So now I want to explain the method that we're going to use to solve an exact differential equation. Today we just explained what an exact differential equation is, and it's related to calculus 3. And now I want to kind of give you the method, and then on the next video, I'll give you some examples on how to use these methods, but we can actually understand what the steps are. The first step to solve a differential equation that is an exact differential equation, or what we think is an exact differential equation, so something like this. In the very beginning, we don't know that it is an exact equation, so we have to check. So verify or check that it is an exact equation. And so what do you do? So this is where we have to take some derivatives, the derivative of m with respect to the y, and the derivative of n with respect to the x, and we have to make sure that they are equal. So that's step number 1. Okay. So now the step number 2, I have that it says follow the schematic diagram or the picture below to find the f. The key word here is this: find the function f. Okay. So step number 1 was basically saying, yes, there is some function f that will give you the m and then the n. Step number 2 is saying find the f. Okay, so that's what I want to show you on the next slide. And then just to kind of finish here, the step number 3 basically is after you find the f function, you just make it, okay, make it equal to constant c. So you get a formula for f, and then at the end of the day, you make it equal to a constant c, and then from there you essentially solve the differential equation. But let me just go back to step number 2. Step number 2 is telling us how to find the function f. So let me just give you the idea here. So the differential equation given to us is something like this. So m dx plus n dy. So what is the first thing that you have to check? You first have to check that the derivative of the m with respect to the y variable, and then the derivative of n with respect to the x variable, you have to first check that they are equal to each other. So if you remember the picture that we have for the calculus 3 idea, So this basically is the same picture. All right, so now suppose that you have done that already, but now that's step number one. Check that these two blue things are equal to each other. Step number two has a few parts to it. So there's several ways to get this. And so what I'm going to do is you go from M to F, and then from F to N. So let me just say it this way. So here's step A, and then here's step B, and then step C is basically you go back to the F. All right, so it doesn't make any sense for now, but that's the idea that we are going to follow to find the F. To find the formula for F, you follow these arrows, but on the next video, I will show you with examples on what those arrows mean. All right, so that's all I want to say today. I want to explain what exact differential equations are, and then where they're coming from, and then how to check whether you do have an exact differential equation, and then I want to give you a picture on how to find the F, and then on the next video, I'll explain how to use this red picture arrow. All right, so that's it for today. I hope this is helpful, and I'll see you next time.